Glow discharge is a type of gas discharge. It can be best seen at a reduced gas pressure. Let's consider the following example. We apply constant voltage of several hundred volts to the electrodes soldered into a 30-50 cm glass tube. Then we gradually pump the air out of the tube. At a certain moment, a discharge occurs in the tube in the form of a luminous cord which connects the tube anode and cathode. When pressure is reduced further, then the cord expands and fills all of the tube's section. The glow near the cathode decreases. At gas pressure of 1/10 of a millimeter of mercury, the discharge looks in the following way. A thin glowing layer, that is the cathode glow or the cathode film, abuts upon the cathode. It is followed by a dark layer, which is called the cathode dark space. Then this dark space transits into a glowing layer, called glowing fluorescence. It has a sharp cutoff from the cathode side. It gradually disappears from the anode side. There is also dark space after the glowing fluorescence. It is called the second or Faraday dark space. The specified parts are called cathode parts of a discharge. The second dark space is followed by a luminous region extending to the anode. It is called a positive column. In some cases, the column disintegrates into several layers or strata. A characteristic feature of the glow discharge is the spatial potential distribution along the tube's length. Almost all potential drops in the discharge occur in the cathode dark space. Such difference of potentials between the cathode and glow discharge boundary is called the cathode potential drop. It is the major property of the glow discharge which distinguishes it from all other forms of gas discharge. The cathode potential drop depends solely on the cathode material and type of gas. It is proportional to electronic work function of the cathode. The mentioned properties of glow discharge reflect the following pattern of discharge-maintaining processes. Positive ions are formed as a result of the electron impact ionization in the glowing fluorescence and the positive column. The ions move towards the cathode. Having passed through the region of the cathode potential drop, the ions acquire a considerable amount of energy. Electrons leave the cathode influenced by the intense bombardment by high-speed positive ions and the photoelectric effect caused by discharge emission. The electrons move towards the anode. They accelerate fast in the region of the cathode potential drop. When colliding with the electrons, gas atoms are ionized. As a result, new positive ions appear. They move towards the cathode and form new electrons, and so on. Thus, electron impact volume ionization and secondary electron emission on the cathode are the main processes which maintain the discharge. The existence of the cathode dark space is explained by the fact that electrons start colliding with gas atoms not right away, but at a certain distance from the cathode. The width of the cathode dark space approximately equals a mean free path length of electrons. The width increases when gas pressure is reduced. Thus, electrons in the cathode dark space move practically without colliding. Concentration distribution of positive ions and electrons in various parts of the discharge is quite different. Positive ions move much slower than electrons, thus the cathode has a much greater concentration of ions than that of electrons. That is why a powerful spatial positive charge occurs near the cathode and causes the cathode potential drop. The positive column has a good electrical conductivity because of a big concentration of electrons. Thus it has insignificant voltage drop. The positive column has both positive ions and electrons. Thus an intense ion recombination occurs here. This explains the glow of the positive column.